Okay, so we've just went over the solution for exam 2. Hydraulic jump day is Tuesday of next week. What that means is come with a little bit of an appetite. There will be cake. If you want to bring more refreshments, that's definitely welcome. I don't know if any of you have gotten a blue wig, but I have a couple, like community wigs, that we can pass around so that everyone can get in the spirit of things. We're going to start here, and then we'll move over to the fluid mechanics lab. And I just hope that there's not another course scheduled at that time. That'd really throw a damper on things. Yeah. All right, so the next thing is the design project phase 2, which is just the reservoir sizing. You'll need to upload that by Tuesday at 3:30. On the subject of the design project, I rescaled the scores for part 1 and part 2. It was originally graded out of 100 points, but if you remember from the handout, I said that part 1 is 20% of the grade, part 2 is 30%, you know, like the weighting isn't uniform, and so I had to rescale it to get those weightings to match up what it says on the assignment handout. So don't be panicking if all of a sudden you see that you got 15 points, whereas before you had 100. It's just 15 out of a 15 is the same as 100%. Yeah. Yep, everything's weighted the way it should be. So if you look at Blackboard right now, that course average that it says is a correct representation of your current standing in the course. Now, there's still the final exam, and the majority of the design project is in the final report. That's 55% of the design project grade. 45% of those points are earned at the draft stage, but what you need to submit is just the spreadsheet for your reservoir sizing. As a rule of thumb, reservoirs are generally sized about 25% larger than the maximum volume that you'd expect to see. So when you go through that process of the daily increase and accumulation of water and then it drawing down, the amount that you find as the maximum amount during the day, assume your reservoir is going to be 25% larger than that. So you can just multiply that volume by 1.25 and then do a linear interpolation for the pricing, because you also, in the final report, need to identify how much that reservoir is going to cost. Any questions? All right. A week from today, Thursday the 6th, that class is going to be online. I'm going down to Clemson again to work on the FE, so I won't be here, but you can watch the video. We're going to talk about momentum today, and you may remember momentum from such hits as the orifice, the contracting orifice, and we calculated the force required to hold the system steady. And we always phrased it in a very specific way because the pressure here that's in the pipe that's cut with the control surface, remember the pipe continues. The water is entering this pipe in an enclosed fashion so that there is some external to what's inside the control volume, an external pressure force that's being applied, P1A1, and then F of X is the force that we would apply to the flanges to hold the system steady. And so what we did in problems like these was we calculated the mass flow rate m dot, which is the volumetric flow rate Q multiplied by the density. And then we found the difference in velocities. And since the diameter is contracting, that means the cross-sectional area is less at 2, which means the velocity is going to be higher. So the whole reason why there's some external force that needs to be applied here is because of the difference in velocities, the magnitude of velocities. So this is what we did back in the days of closed conduit flow. Now in open channel flow, there's also momentum. And there's both of those two components of momentum. There's the part of momentum that's related to external forces being applied to the control volume. So if we consider the water that's in this is water flowing downhill, and the depth is changing, just to make the point that this is non-uniform flow, and so momentum is conserved even when you have non-uniform conditions. And so at location 1, where the depth is shallow, there's some water on the other side of this water. This is just the water that's in our control volume. We're analyzing this element of water. The water on the other side is pushing on it with a force equal to the depth to the centroid, the area, and the unit weight. Now, this first component here is the dynamic component of momentum. It's related to the movement of the water, the fact that the water that's here has some velocity. Now, the units are a bit odd right now. If we multiplied both sides by the unit weight, then you'd get the units of force there. And let me write that on the board just because the units are a bit counterintuitive. If we have q squared divided by GA, then the units for that, for q squared, is going to be meters to the 6th divided by second squared. So that's the units of flow rate squared. And then G is meters per second squared, and I put a second squared up in the numerator since it was in the denominator of something already in the denominator. And then the units of area would be meters squared. So the second squared is both the numerator and the denominator. That cancels out, and what we're left with is meters to the cubed. Now that's when it's just in the momentum form of it. So that if we multiply that by the unit weight, gamma, so if we take meters cubed and we multiply it by the units where gamma has units of newtons per meter cubed, then what we end up with is newtons. So the point is that we go through this momentum function, multiply it by gamma, and it becomes a force. For the benefit of those watching at home, let me pull up the examples because I have that same stuff that I just showed on the board, the units. I wouldn't want anybody to miss out on a good units analysis. All right. Any questions about the units of momentum? Okay. So the two components of calculating the force in open channels from momentum, the dynamic force and the hydrostatic force, related to the movement of the water and the forces on the outside of the control volume. So why we care about momentum is related to hydraulic jumps. And Tuesday is hydraulic jump day, so I figure you probably better learn a little bit about that before it occurs. Hydraulic jumps happen when there's some sort of a change in flow that forces supercritical flow to become subcritical flow. In this first picture, what this is showing is we have a really steep slope. The slope initially is so steep that it's causing supercritical flow. And that slope that causes critical flow is S sub c. So here at 1, the slope is steeper than the slope that causes critical flow. So you know that it's supercritical because in this drawing they're showing you where the critical depth should be, and our depth is less than the critical depth. So that confirms here that the slope is supercritical. But then it's transitioning to a subcritical slope. And the way we know it's subcritical conditions downstream is that our actual depth of flow is more than the critical depth of flow, what the critical depth should be. That's what this dashed line is. And so anytime you have flow that transitions from super to sub, there will be a hydraulic jump. And here, that's showing that the hydraulic jump maybe is upstream of the transition, maybe it's downstream of the transition. It can actually be in both places depending on the exact depth of the downstream. So here's one instance that can cause it. Another situation that actually is what we're going to have in the lab, what causes supercritical flow for us is flow coming out of an underflow gate. And so when you put a gate in place, that forces the water to pool upstream because the water has to accumulate enough energy upstream to come very quickly under the opening that is available. So you force a pooling upstream, and so now the water is going supercritical downstream of the gate, but it shouldn't be going supercritical because if you look at the slope here, this says that the slope is less than the critical slope. So we've got a relatively mild slope, and so it can't keep up the supercritical conditions forever. And you'll notice that the depth is gradually getting larger and larger. The depth is increasing, but then it goes through this transition at a very specific time. It goes through this transition when the upstream depth is equal to the sequent depth that's downstream. And you don't know anything about that yet, but you will at the end of class today. There's this normal depth that water should be flowing at in the channel, and it'll go through this jump when upstream of the jump it matches the depth that has the same momentum as downstream of the hydraulic jump. We're going to get into doing calculations about that today. So there's actually a couple of things happening here. There's gradually varying flow as this depth is increasing, but then there's rapidly varying flow at the hydraulic jump. And so here RVF stands for rapidly varying flow, and that means a hydraulic jump. Gradually varying flow we'll talk about after hydraulic jumps, and we have to go to kind of a lot of effort to calculate the rate at which water makes these gradual transitions. Here's another instance where you could have a hydraulic jump. Here we've put a gate into place, and it's a supercritical slope. And so it's going to stay supercritical after the gate. That's no problem. It's just gradually varying flow after the gate. But before it, because we've impinged the flow a little bit, there's pooling at the face of the gate, and so the water is going to go through a hydraulic jump just until it matches the flow that has choked upstream of the gate. So that's a little bit less common. And then, of course, there's supercritical flow coming down off of spillways. And this is, in terms of physical systems, you'll see this a lot on dams. The water picks up a lot of energy as it's flowing down the face of a spillway, so it's supercritical conditions, but then the river or whatever channel downstream that's accepting the flow over the spillway is going to have a mild slope that's less than supercritical slope, and so it'll have to go through a hydraulic jump. And there's a lot of energy that's being lost in a hydraulic jump, and it can really tear apart a channel. And so when spillways are designed, there's usually pretty extensive thought put into placing big blocks of concrete to absorb some of the energy to try and limit the amount of scour that's going to occur with the hydraulic jump. Any questions so far? The gradually varying flow is any time the water depth is changing that it's not a hydraulic jump. The hydraulic jump is the rapidly varying flow, but the gradually varying flow is after this gate as it's slowly transitioning back to the normal depth. Gradually varying flow is approaching this choke as the water goes from the normal depth to some choked depth right at the face of the gate. And even as it's supercritical conditions, it's gradually varying until it meets the sequent of the downstream depth. So this is what we call a momentum depth diagram. And it looks similar in shape to the specific energy diagram that you saw before, but it's actually something completely different. I want to emphasize that this isn't a specific energy diagram, and to emphasize that, we're going to open up Excel and calculate both a specific energy diagram and a momentum depth diagram and see how they're different. The momentum depth diagram is a graph of the momentum function. And so for a certain flow rate, you can have a lot of different depths. And those variety of different depths are what causes this curved shape. You can have depths that are supercritical and depths that are subcritical. So there are some similarities here between the specific energy diagram and the momentum depth diagram. The minimum point does correspond to a critical depth. So you can still use a momentum depth diagram to find out if your flow is super or subcritical, because any conditions that are more than the critical depth are subcritical flow conditions, and any depth that's less than critical depth is supercritical. But what this graphically can be useful for is finding how deep the water is going to be on either side of this hydraulic jump. Because here is supercritical conditions. You could take this line up and from your supercritical momentum find out what is the new conjugate depth. Sometimes that's also called a sequent depth. What it means is it has the same amount of momentum and it's the same flow rate or discharge, but it's a different depth. Now, energy is not conserved through hydraulic jumps. There's a lot of energy lost in the turbulence of that roiling flow. But what is conserved through the hydraulic jump is momentum. So that's why we use a momentum depth diagram, is because graphically it allows us to find the downstream depth y2 after a hydraulic jump. So let's try this out. If you have Excel with you, you can follow along. If you don't, you can just watch and be less amused. We're going to calculate. There's online a starting file, just so, I mean, you can start from scratch if you like, but if you go to the course web page, under there's a folder that says some spreadsheets, some class spreadsheets, something like that. Oh, this computer's just miserable. It's so slow. Yeah, that one's pretty bad too. Okay, so if you go to Blackboard, then you can get the starting file for this. I'll leave it up so that you can do it later if you like. Under selected Excel files from class, it's the second one, momentum depth diagram. So here it is, our download. What we're going to do is we've got flow conditions where it's a rectangular channel. The depth is going to be varying. Our width is always going to be 6.5 meters. The flow rate that we're sending through this channel is always 15 cubic meters per second. So just to start things off, let me ask you, how is it possible that you could have many different depths if the width and the flow rate are always going to be the same? What's causing all those different depths? Yeah, but why is the velocity changing? You're right, the velocity will be different. But what would cause different velocities? Different slopes, exactly. Yeah, so I don't want you to think that just willy-nilly the water can flow at any depth that it wants. No, if you have a steep channel, then the depth is going to be short because you have a high velocity. If you have a mild channel, meaning a relatively low slope, then that's going to lead to slower water velocity and deeper depths. All right, so with this starting file, what we're going to do is calculate both the energy and the momentum. All right, so I've just selected, based on creating a nice looking graph, a variety of depths. You don't necessarily always know what the starting depth and ending depth should be until you actually start graphing it. So it's not always going to be 0.2 as your beginning depth and 4 as the starting. You may need to make adjustments on the fly, but for purposes of illustration, we'll do these. Now, h bar is the depth to the centroid. And in a rectangular channel, the depth to the centroid is just from the water surface halfway down to the bottom. And so it's going to be easy in this case, because the depth to the centroid is just the y divided by 2. All right. So then I can drag that down and apply the formula everywhere. Anybody want to hazard a guess why we're looking at the depth of 0.816? Good guess. You're right. Yeah, that's going to be the critical depth. Just coincidentally, it worked out that way because I thought that'd be a nice depth to graph. So the area here is going to be the width times the depth. Okay, so we've got the area, and then the velocity at each of these different depths will be the flow rate divided by area. Q equals VA, so V is Q divided by A. So the velocity is progressively getting lower and lower. When we have deep water, it's because you've got a shallow slope. You know, when you're trying to convey a certain amount of water through a channel, if the slope is shallow, that means the water is going to be very deep and you need a very tall channel to do it. But if you've got a high slope, then the water doesn't need much depth to convey that same amount of flow. Now energy, we're going to use this equation for energy, this one. It's going to be the depth plus the velocity head. So V squared divided by 2G. All right. So then I can apply that all the way down through. And then the momentum equation is going to be the flow rate squared divided by G divided by the area. And then adding the area times the depth of the centroid, h bar. Okay? And then we'll just add the momentum function down through. Now here in the graphs, miraculously they appear. Okay, so on the left one here is the energy, specific energy diagram, and here's the momentum depth diagram. So you use the specific energy diagram if you had like a step down or a step up and you wanted to find out what will be the new depth in response to that change. The momentum depth diagram, you would use this for a hydraulic jump. Two different applications, but now you know how to make both. Any questions about that? Okay. Oh, I guess I wanted to calculate the critical depth here. Let's do that, just to show that, you know, where that came from. So the critical depth would be the flow per unit width. So 15 is the flow. The unit width, the width of the channel was 6.5. Okay, and I need to square that. And then divide it by G, 9.81. And then I also need to put in the parentheses because I'm going to take everything to the 1/3 power. Okay, so the critical depth is 0.816. And so what that means is, here on this diagram, there's the supercritical portion of the momentum depth diagram below the critical depth. So anytime we've got flow less than this 0.816, we have supercritical conditions, and it'll go through a hydraulic jump up to the subcritical. Now, there isn't anything as dramatic as a hydraulic jump when you have subcritical flow transition down to supercritical flow. And sometimes that can occur if you've got water approaching a drop-off, for example. There are other things that cause it, and we'll go into a lot of detail about what kinds of features can cause gradually varying flow. But if you have subcritical and it's approaching this drop-off, then it will go through a period where you've got maybe supercritical. Briefly. So this was sub, and it's not dramatic. It's just a gradual transition. The only time it's dramatic and a big jump, a hydraulic jump, is when you're going from supercritical flow that can't be sustained anymore based on the shallow slope, and then it has to jump up to meet its conjugate depth. That's right. You got it. So the hydraulic jump has an upstream depth and a downstream depth. And you can find the new downstream depth by graphing the momentum function like we just did in the example and solve it graphically. There's also a momentum equation where you can do it numerically. I'll show you that in just a minute. But it's important to remember how to calculate the Froude number because the Bellinger momentum equation, which you'll see in just a moment, makes use of the Froude number. Now, this is the version of the Froude number that you should use if you have, it'll work for any kind of flow channel, whether it's trapezoidal or triangular or whatever else. But if you have a rectangular channel, then you can calculate the Froude number this way, only if it's rectangular. Because you'll need the Froude number for the Bellinger momentum equation. Now, I've got a couple of videos showing hydraulic jumps, but they are QuickTime videos, and I'm not sure if that's going to work in here. So let's just give it a try. There we go. What have we got? Maybe VLC. Usually works. All right, so this is someone's doing the dishes, thinking about fluid mechanics, as we all do, right? All right, so the water's coming out of the faucet and it's hitting a flat plate, and the water has velocity. So when it hits the plate, right now the water isn't, it's not flowing very fast, but they're going to turn up the, they're going to turn the handle and increase the flow rate and therefore increase the velocity of the water. And watch what happens as they do. All right, so now the water all the way around this rim, that's supercritical flow, and it can't be sustained on a flat surface. As the water is slowing down, then it reaches its sequent, goes through the jump, and now the water is expanding radially. It's kind of hard to think in radial terms sometimes. You know, we usually just have these cross sections. But here the water is moving outward away from the stream, and it's a hydraulic jump. So you don't have to have access to a flume to witness the beauty of a hydraulic jump. You could make one at your house today. But I'm certainly not suggesting that you do dishes, because I know that is not like at the top of anybody's list, especially when you're in college. So they can adjust the location of the jump by varying the flow rate up and down. And this guy's so into it he can't even resist touching it. So, and now the flow rate's so high that the hydraulic jump, I don't know. You get the idea though. Supercritical flow, all around it is subcritical flow. Any questions about that? Okay, yeah, it is cool. All right, let's open the other one. This is a little bit larger scale. This is water coming out of a dam. And this is one of those cases where the water has a lot of velocity, because in this case it's coming from an underflow gate. And so it's supercritical conditions, but it can't be sustained. And this is in a chute that's specifically designed for a hydraulic jump to occur. It's a really heavily armored concrete, because you look at this roiling water, it's really turbulent, and there's a lot of energy being dissipated there. It would just tear apart any kind of an earthen channel and send that sediment downstream. So here we're seeing a hydraulic jump in its more natural environment. Well, not natural. It's an engineered system, but it's not somebody's kitchen sink, is the point. Okay. So you can do it graphically by graphing the momentum function. And here's one illustration of how you could do that. Let's say, for instance, that we made a table of the momentum function, and then we graphed the momentum function, similar to what we just did in class. And we knew that we had an initial depth at 1 of 0.6. I assume that these are meters. I don't know. It doesn't say. So we have an initial depth of 0.6. So you'd come over from the y-axis, find the intersection with the curve. So that's a supercritical depth initially, which means that eventually it's going to jump up to its sequent or conjugate depth. And that conjugate depth, we can come over here to the y2 and find out that it is, it looks like about 1.4 is the conjugate depth there. So we are trying, the point is you're trying to find the momentum, the same amount of momentum. So here it was 5.33, so it looks like it's going to be between 1.2 and 1.5, where it has that same amount of momentum. You could solve this using goal-seek on Excel. You know, you could keep changing this depth. See the cell where it says 1.5? You could do a what-if analysis. No. Yeah, goal-seek and tell it, keep changing this depth until this momentum, the one that says 6.01, keep changing it until it equals 5.332. And then that would tell you what is the depth that matches the same amount of momentum that existed upstream. So where's most of the momentum in the supercritical depths? Because the momentum, remember, is in two places. The momentum is the dynamic component of the momentum and then the static component of the momentum. So here in the supercritical range, where the depths are low, where's the momentum? It's mostly in the dynamic term. And then on the other side of things, on the other side where you've got the larger than critical depths, then the majority of the momentum there just exists as the static term. So here it is. This is called the Bellinger momentum equation. And it allows you to find the depth at 2 downstream of the hydraulic jump by knowing the initial depth, y1, and then the Froude number at location 1. Another way to solve this, instead of calculating the Froude number at 1, you can substitute in the depth, the critical depth relative to the depth at 1. Make note of the fact, though, that then you're cubing it, rather than here it's squaring it. And so that's one of the commonly made mistakes, is people getting used to the Froude number and squaring it, but then switching over in one instance to the ratio of the critical depth and the upstream depth, and then forgetting to cube that. Now, there are some assumptions here that you need to be aware of. We're not going to see perfect behavior in the lab when we're actually measuring the hydraulic jumps and comparing how good is this equation to what we actually measured. We'll see some variation, because this assumes a uniform velocity distribution. By that, I mean, remember when we were talking about the no-slip condition in fluid mechanics? I would say, here's the water, and the water is not moving very fast near the near the bottom of the channel, but it's gradually getting more and more the further away we get from the bottom. And so there's this curved velocity distribution. This is reality. Unfortunately, the Bellinger momentum equation assumes, instead of that, the Bellinger momentum equation assumes that the water is slipping over the surface prior to the hydraulic jump. It's an easy to use equation, but you kind of are at the mercy of its poor assumptions. And so if you have a particularly rough surface or a really shallow channel, then that's where you're going to see the impact of reality not matching that assumption. But if you have relatively slow-moving water, well, I guess slow-moving water won't be supercritical, but if you have a deeper channel rather than a shallower channel, then this will be less of a problem. It's also assuming hydrostatic pressure distribution as you go down through the water. Since the water is moving, It won't be exactly hydrostatic, but it'll be pretty close. And so this second term isn't so much of a problem. It also assumes that the channel is horizontal, that there's no elevation difference between location 1 and location 2. And often it's pretty close to being horizontal, but it won't be exactly horizontal. And so some of the error in measuring the depths is because actually the elevation of the channel bottom isn't the same at 1 and 2. Now, related to the velocity distribution assumption, this assumption of boundary shear stress is negligible. So that's saying that the water at the bottom isn't resisting flow. So it goes hand in hand. In this reality of the no-slip condition, we know that there is a shear stress applied by the channel to the water. As the water is trying to move one direction, the channel is pushing back against that water movement. But the Bellinger momentum equation assumes that that's not happening. There's also energy loss. Yeah, go ahead. There are empirical correction factors that have been developed that do account for things like that, yeah. And they're published in technical papers. It's not anything that you'll find in a textbook, though. The only thing you'll find in a textbook is this sort of idealized case. Usually, if you remember the video I showed you of that, the real-world flume, where that jump was occurring, you'd calibrate something like that in the lab in order to know what the depth would be downstream when you scale it up to reality. So if you want to quantify how much energy was lost, here's the formula to do it, the delta E. And it's going to give you units in terms of meters. The energy loss will be in terms of meters. And so we can do a specific energy diagram. And if we know the before depth and the after depth, then graphically that delta E is simply the difference in specific energy. Or you can calculate it this way, according to the formula that's on the screen there. So momentum is conserved through a hydraulic jump, but energy most definitely is not. So I'd like you to get a chance to try the equation today. Let's say that we have an upstream depth of 0.86 meters, and this is a rectangular channel. So that makes it easier to calculate the Froude number. Let's go back to the Froude number equation. I'll put that on the board so you've got it accessible there. You can go old school and say the Froude number is the square root of q squared times the top width b, g a cubed, or you can try out that the Froude number is lowercase q, flow per unit width, divided by y1 times g, square root of g y1, which is also equal to the velocity at 1, square root of g y1. All right, so there's the Froude number equation. Let's go here and apply that to finding out what is the new downstream depth under these conditions using the Bellinger momentum equation. And now this is asking the fraction of the initial energy that's lost through the jump. By fraction, that means find the difference in energy. That's part of it. But you also want to know how much energy was there at 1. So you're going to know the ratio of delta E to E1 in order to know the fraction of the initial energy that's lost. Okay, the downstream depth should be about 5.96 meters, and I calculated the Froude number two different ways. I did it based on the flow per unit width, which only works for a rectangular channel. Don't use this for a trapezoidal channel, like you'll probably see on the exam. Use this version if it's a trapezoidal channel, the full version of the Froude number. Same number either way. And then you substitute it into the Bellinger momentum equation, and we get the new downstream sequent depth. Now, the fraction of the initial energy that's lost, the initial energy is going to be the depth plus the velocity head. That's how you calculate the initial energy at 1. And then the delta E is going to be based on this formula. Okay, so here's that. Calculating the energy loss. The difference in the depths cubed divided by 4 times the product of the depths. So we're going to lose 6 meters, more than 6 meters of energy through that jump. And there was only about 12.6 meters of energy initially at 1. So that, as a fraction, is 51% of the initial energy is going to be lost through the hydraulic jump. And sometimes that's a good thing. Sometimes you're trying to dissipate energy. And so hydraulic jumps are forced to occur in a certain location where you can control the conditions within that location. You don't want the hydraulic jump to happen some, miles downstream in a channel where it may scour channel, but rather you have it in a place that's kind of armored and you have blocks in place to absorb some of the energy. We'll look at a video on Tuesday of a hydraulic jump in Germany that's in a river. It's naturally occurring, and people surf on it. It's actually, yeah, it's similar to, has anybody here gone whitewater rafting before? When you're going down the, probably both of them, I've done the New and the Golly, like sometimes they'll swing you around and like you paddle to get into a certain spot, but then you can stop paddling and you're just sort of like sitting there. And that's a standing wave. Hydraulic jumps are sometimes called standing waves when they occur in rivers. In a standing wave? Did you have a helmet on? Yeah. Okay. Yeah. You're a rebel. Don't do that. All right. Usually they give the beer out after the rafting trip, not before. Sounds like they switched it this time. All right, so we could solve that same problem using Excel, where we're trying to find out what's the sequent depth. So we could have a spreadsheet where we've got the Q in terms of cubic meters per second. We've got the channel width in terms of meters, the depth in meters, H bar, which is the depth of the centroid, the cross-sectional area. We've got the velocity and the energy, and then the momentum function. Okay, so this example we had 123 cubic meters per second, and if we wanted to focus in on the width was constant, it was always 9.4 meters wide in this channel. Okay, and then the depths, let's just look at a variety of depths starting at 0.2 through 8. I'll do 0.3, then 0.5, then 0.86, then 1, 1.5. All right, so the H bar is, for this rectangular channel, just going to be half of the depth. And then the cross-sectional area is going to be the width times the water depth. And the velocity will be Q divided by area. And then to calculate the energy, which we're going to need to solve for how much energy change was there, it is the flow depth plus the velocity head. So v squared divided by 2g. Okay, that's a lot of energy. And then the momentum function Let's get that off of here. Here's what we're going to use for the momentum function. Okay. It's q squared divided by g divided by the area plus a times the depth of the centroid. All right. Okay, so our initial, in this problem, we initially had the upstream depth of 0.86. So here is our initial depth, 0.86. And so what we want to do is we want to find out where is it that we've got the same 194 momentum function. So that's getting pretty close to it here at the depth of 6. So let me do this what-if analysis here, data, what-if analysis, goal seek. I want to change this depth, I'm going to change the momentum function to 194.248 by changing the depth. So it will iterate that depth until it matches. So it gets 5.95, which is the same as what we had when we were solving it. We had rounded off a little bit more, 5.956. So it matches. And then as for the delta E, here was our initial, right, and here was our final. So the delta E is just going to be the difference between the two. So delta E is the initial energy that we had here minus the final. Okay, so the delta E, 6.45, same as we got before. So it all works out. Excel can be used, or you can use the Bellinger momentum equation. The momentum equation is probably simpler. Okay, trapezoidal geometry. Any questions before we move on from this example? All right. The reason why we're revisiting trapezoidal geometry is to emphasize how you can find the depth to the centroid in a trapezoid, because it's not halfway to the bottom. Why not? In a rectangular channel, that's all we did. We said y divided by 2 is h bar. But here, how come I'm not saying y divided by 2 for the h bar? Because it's got sloped sides. Yeah, so does that mean you're going to have to go deeper to get to the depth of the centroid, or it's not going to be as deep as compared to if it had been rectangular? Not as deep, right, because more of the area is close to the surface than if it had been rectangular. All right, so what this example shows is how to find the depth of the centroid. Let's say that we have a channel, it's a 1-to-1 side slope, and the bottom width is 3 meters. What does that mean the top width is going to be? If you've got a bottom width of 3 and 1-to-1 side slopes, the top width's going to be 5. Exactly. Yeah, because if we do a little sketch of it here on the whiteboard, we've got, okay, here's the, boy, that's terrible. All right, that's a depth of 1, and that means this side top width is going to be 1 on either side, and so it's 3 at the bottom and it's 3 on the top, and so overall the total top width is 5. So see if you can find out what is this formula solves for the distance from the bottom to the centroid. So I want to know what is the depth to the centroid. Here's a formula that will tell you the distance from the bottom of the channel to the centroid. But then the last thing you need to do after applying this formula is convert that from bottom up to top down. All right, so we want to find the depth of the centroid here. The distance up to the centroid is 0.5417. I forgot to write it in here, so therefore h bar, which is the depth to centroid, will be 1 minus that distance that we found, 0.5417 meters. So that is 0.4583 meters. That's the depth to the centroid. And you'll need to be able to do that, I think, for the homework assignment. I think there's a hydraulic jump in a trapezoidal channel. So that's how you can do the h-bar. Let's take one last look at the announcements here. All right, so on your plate is getting ready for the submission of your reservoir sizing. That's the Excel spreadsheet you need to upload to MU Online. Then on Tuesday, we're going to look at a hydraulic jump in the lab and talk more about hydraulic jumps. Then Thursday is the homework assignment, uploading it online by 3:30, but we won't actually meet. So I will see you Tuesday. Have a nice weekend.